They called it a flying milk bottle, a squat, bulbous silhouette that seemed to mock every aerodynamic principle a Luftwaffe pilot had been taught. Yet beneath that ungainly shape, parked on a grass strip in August 1943, sat a machine whose combination of engineering detail and industrial backing presented a single chilling fact. This was not merely another fighter. It was evidence, arithmetic in metal, that one side of the war enjoyed a margin Germany could not meet. A captured P-47 Thunderbolt had landed intact at a remote Luftwaffe field. Its American pilot was taken into custody. The airframe, surprisingly whole, was pushed into a maintenance bay. The unit's aeronautical engineer, Schulz, first name undefined, was sent to inspect and to report. What began as a curiosity quickly turned into a methodical investigation of systems, materials, and numbers. Over the following days, Schulz cataloged parts, weighed components, took measurements, and did the kind of arithmetic an engineer does when asking the question, how and why does this work? From the outside, the P-47's bulk suggested brute force. A thick fuselage, wide landing gear, and a round, air-cooled engine cowling that looked more like a truck than a fighter. German pilots joked about its looks. Their shorthand turned to contempt. But Schulz, working with calipers and a careful eye, read a different text. The aircraft's shape and the way its systems were laid out were less about aesthetics and more about an integrated philosophy: power, survivability, rapid repair, and production at scale. If you value detailed technical history, subscribe for more. This channel digs into the engineering choices that changed battlefields. The heart of the revelation was the engine. Under that round cowling sat a Pratt & Whitney R2800 double wasp, 18 cylinders arranged in 2 rows of 9. Briefly, a radial engine is a piston engine with cylinders arrayed in a circle around the crankshaft. The design trades a slimmer frontal area for simplicity, cooling advantages, and, critically, robustness. The R2800's architecture gave an immediate read. This was a powerhouse designed for high output and for being made in quantity. Schulz estimated the unit's output at roughly 2,000 horsepower from original machining marks, stamped tolerances, and the materials used in the crankcase and connecting rods. Those numbers were not fantasy. They were derived from measurements of rod journals, crankshaft dimensions, and metallurgical clues visible even in a captured airframe. What stood out was not just peak power, but the way that power was delivered: sustained, reliable, and available at altitude. Where German radial engines had been pushed and innovated, they often ran into manufacturing bottlenecks. Shortages of high-grade alloys, complex cooling or supercharging systems that were difficult to reproduce in mass, and compromises introduced under resource pressure. Schulz observed the R2800's components had been machined to relatively tight tolerances and made from alloys specified for both heat resistance and fatigue life. In practice, that meant an engine that could be run hard and repaired in the field rather than scrapped when stressed. But raw horsepower alone does not win fights at 25,000 feet. What made the P-47 exceptional at altitude was the way that power was kept available where others lost it. A production-proven turbo supercharger system routed through the fuselage to a rear-mounted turbine. A turbo supercharger uses exhaust gas energy to spin a turbine, which, through a compressor, forces more air into the engine, preserving oxygen mass at altitude. In the P-47, the exhaust flow was collected, ducted rearward, and used to drive a turbine positioned aft, a long, hot plumbing job that required heat-resistant ducting, durable bearings, and precision-engineered seals. Conceptually simple, the execution is brutal. Long, high-temperature runs, variable pressure, and rotational speeds measured in tens of thousands of RPM at the turbine. The engineering challenge lies in materials that can survive sustained heat cycles, ducting that resists expansion and leakage, and bearings that can tolerate thermal distortion. Schulz inspected the ductwork and the turbine housings and noted a level of practical conservatism. Components that were not the lightest possible, but that were overbuilt for durability. The Americans accepted a weight penalty in exchange for reliability. The result was that P-47s could maintain rated power well above 25,000 feet, a ceiling where many German fighters experienced significant performance drop-off. The turbo supercharger was not an experimental add-on. It was a production-proven subsystem, integrated into the airframe and supported by manufacturing lines capable of building thousands of units. That combination, high output, durable engine plus a production-grade turbo system, produced a tactical advantage. In air combat, altitude confers energy and time. An aircraft that retained engine power at altitude could choose the fight, dive with speed, and recover without losing its engine's performance. Against opponents whose engines sputtered or lost boost above 20 to 25,000 feet, the P-47's sustained power translated into positional superiority more often than a single technical spec would suggest. Design choices extended beyond horsepower and boost plumbing into repairability and survivability. The P-47 was, by design, modular and forgiving. Schulz's notes emphasize removable cylinders, a straightforward carburation and ignition layout, and an airframe built to accept heavy loads and damage. Removable cylinders mean quick replacement in a field shop. Instead of replacing the entire engine or sending the aircraft back to a distant depot, mechanics with hand tools could unbolt and swap a damaged cylinder and head assembly. In wartime, that modularity multiplied aircraft availability. The P-47's radial engine was inherently tolerant of combat damage in a way that liquid-cooled inline engines were not. An inline engine, when its coolant lines are ruptured, can overheat and seize in minutes. A radial with no centralized cooling circuit can sustain punctures and keep running long enough to return to base. The airframe itself reflected a philosophy of robustness. Thick-gauge aluminum skin, redundant control runs, and significant cockpit armor placed where it would save the pilot's life were all present. The aircraft was designed to take punishment. Reports, summarized in German damage logs and corroborated by Allied records after the war, repeatedly noted P-47s returning on one engine with shredded wings or with entire control surfaces disabled, yet still making it home. For German pilots flying lighter frame designs, the same hits were often catastrophic. Armament was another area where the P-47 reflected a specific strategic calculus. 8.50 caliber Browning machine guns, fed from a combined ammunition capacity of roughly 3,200 rounds, made for sustained, destructive firepower. A single long burst could shred the lightly built fuel tanks and fabric-covered control surfaces of many German fighters. The combined rate of fire, when the guns were synchronized and aimed, amounted to scores or hundreds of rounds downrange in a single pass, an output that overwhelmed designs built around short, precise bursts. Tactically, the implication was straightforward. P-47 pilots could engage in boom and zoom attacks at altitude, dive with high energy, deliver heavy, sustained fire, and climb back to altitude while maintaining engine performance. Lighter German designs were optimized for agility at lower weight. Against concentrated 50 caliber fire and the altitude game, their vulnerabilities were exposed. The Americans did not rely solely on pilot skill or clever tactics. They fielded aircraft that could survive hits, return to fight, and be rapidly turned around in service depots. All of these details, engine design, turbocharging, modularity, armor, and armament, were meaningful only because factories turned them into numbers. Schulz's calculations moved from measurements of parts to the arithmetic of output. He had, in hand, production figures and notes about ramp rates. Republic Aviation, the P-47's manufacturer, was producing in the hundreds per month. Operational documents referred to a production rate of 500-plus P-47s per month, with plans for increases. Pratt & Whitney's R-2800 production ran into the tens of thousands. Declassified records and post-war inventories later showed engine totals well into large five-digit counts, figures Schulz regarded as conservative in his report. two numbers crystallized the strategic picture for Schulz. First, the aircraft production flows, tens of thousands of engines and thousands of airframes each year, meant the Americans could accept higher loss rates while continuing to grow their effective force. Second, the ratio of Allied to German aircraft production in 1943 was, in broad terms, roughly 3-to-1. Those ratios are arithmetic. They do not lie or lend themselves to rhetorical spin. In context, they meant Germany could not hope to match attrition with manufacturing because materials, labor, and factory capacity were simply insufficient under wartime constraints. Schulz translated this into an operational prognosis. Tactical changes could blunt the P-47's effects in the short term: more head-on passes, concentrated attacks on vulnerable systems, refined formation discipline, but tactics alone could not correct an imbalance rooted in steel mills, foundries, and assembly lines. The German High Command received the report. It was sober and technical, careful to separate immediate countermeasures from long-term structural problems. And then, by several accounts and corroborations and subsequent documentation, it was filed away. Ideological resistance to accepting material constraints, internal political dynamics, and competing priorities all contributed to a dismissal that Schulz's calculations regarded as dangerous. This institutional reaction was not an aberration, but a pattern. Wartime organizations filter bad news in predictable ways. Reports that stress resource incompetence or production gaps are often labeled defeatist. Warnings that require industrial sacrifice clash with political narratives. The names that surface in the record as contemporaneous voices, figures such as Canaris, Speer, Golland, and Sepp Dietrich, appear not as collaborators in a conspiracy, but as parts of a complex bureaucracy where intelligence and industrial reality had to fight for attention. Schulz's technical conclusions were not denied on engineering grounds. They were shelved amid a larger refusal to reorient national priorities toward the kind of mass production the P-47 embodied. The operational consequences were, over the months that followed, plain to pilots on both sides. P-47s and other U.S. fighters began to frequent higher altitudes, to escort bombers further into German-held skies, and to impose a cost on Luftwaffe aircraft that Germany could not meet in kind. Attrition rates among German fighters rose while replacement rates lagged. Post-war declassified numbers largely confirmed the scale that Schulz had conservatively estimated. American engine production in the tens of thousands, more than 15,600 P-47s produced over the course of the war, and ramped monthly outputs that allowed an Allied air arm to regenerate faster than the Luftwaffe could. It is crucial here not to fall into monocausality. The P-47 alone did not win air superiority. Doctrine, pilot training, logistics, radar, strategic bombing, and many other factors all combined. But the P-47 exemplified a design philosophy that, when paired with factory capacity, turned into a decisive edge. Robustness, maintainability, and volume matter as much as technical ingenuity. A well-made plane available in mass can sustain operations in a way that an equal performance aircraft made in limited numbers cannot. Schulz's arithmetic offered a wider lesson about industrial warfare. Engineering choices are embedded in supply chains. The selection of a heavier airframe or a more conservative alloy is an economic and logistical decision as much as a technical one. The Americans chose, implicitly through procurement and production policy, to accept heavier aircraft that were easier to make and repair at scale. Germany, constrained by resource scarcity and discrete industrial bottlenecks, pursued high-efficiency designs that taxed limited materials and required more skilled labor per unit. Both approaches are rational. The difference lies in whose industrial base could sustain which strategy under the pressures of total war. The captured P-47 thus served as a physical manifesto of that difference. Its astonishing power was not a secret hidden in a single component, but a compound effect. The R-2800's horsepower and reliability, the turbo supercharger's high-altitude sustainment, modular repair features that kept aircraft returning to service, armor and redundancy that preserved crews and airframes, and an industrial engine that could produce tens of thousands of power plants and support infrastructure in numbers Germany could not match. There is a human cost to this arithmetic. When intelligence is sidelined, when an engineer's sober calculations are labeled defeatist, the consequences are measured not only in maps and tonnage, but in the lives of pilots and mechanics who must operate under the reality those numbers describe. Schulz did not seek to assign blame in melodramatic terms. His report was an engineer's plea to planners to reckon with material constraints. That plea was, in institutional terms, expensive and uncomfortable. It would have required a reallocation of resources and a political willingness to accept short-term pain for long-term survivability. In the months and years after the captured P-47 was examined, the evidence that Schulz had read so carefully accumulated. P-47s continued to return from missions that should have been fatal for less robust fighters. American factories kept producing engines and airframes. The numbers that were once just figures on a maintenance report became a strategic tide. Post-war analysis and declassified production records validated many of Schulz's estimates. The practical effect of having tens of thousands of engines available, of being able to turn aircraft around quickly, and of accepting a slightly heavier but far more repairable platform. When one returns to the captured machine on that grass strip in August 1943, two images remain. The first is the crude outward impression, the milk bottle, the heavy, ungainly shape that triggered jokes and dismissive glances. The second, far more consequential image is the interior arithmetic. Tolerances on crank journals, the length and insulation of turbo ducts, the spare parts catalogs stacked in a production planning office, the monthly shipping manifests leaving a factory. The first image invited scorn. The second, when read correctly, predicted outcomes. The P-47's astonishment, then, is double-edged. It is the raw kinetic power of an engine and guns, but it is also the power of a nation that chose to convert industrial capacity into reliable, maintainable machines at scale. That coupling of engineering and industry acted like a multiplier on the battlefield. For those who saw it up close and did the math, like Schulz, the implication was unavoidable. In an industrialized total war, factories could decide more than doctrine alone. History rarely offers single moments of revelation. Yet an intact P-47 at a Luftwaffe field, cataloged by a careful engineer, functioned as one of those moments. It distilled into bolts and ducting a lesson about how wars are won and lost, not exclusively by heroism or cunning, but by the quiet sum of parts, tolerances, assembly lines, and the willingness to accept short-term weight penalties for long-term resilience. If you found this technical historical analysis useful, there's much more to explore. Deeper dives on the R-2800's development, the logistics of Allied engine production, and comparative studies of wartime manufacturing philosophies. For sources, start with Republic Aviation production records, Pratt & Whitney engine archives, and declassified German intelligence summaries that examine captured equipment. And if this examination of the P-47's astonishing power changed the way you think about the role of factories in warfare, share it with someone who appreciates the hard arithmetic behind historical outcomes. They called it a flying milk bottle. What German engineers discovered inside was not a miracle weapon, but an industrial truth. When engineering choices are backed by the capacity to build, sustain, and replace, those choices become a kind of power that reshape the battlefield.